This is a good day. We are reaching the ultimate, what do you want to call it? The mountaintop. We've been solving systems of linear equations for a long time, and now in lesson 41, I'm going to show you some real world examples. Not just real world examples, but real world examples, like a circuit. That's real. That gets really real. So I got 4 examples, 3 cool ones and, well, 1 boring one. But I have to do the boring one. You'll see why. But anyway, let's start the cool ones. Like, this is cool. It's an electric circuit. This has called a Wheatstone bridge, and doesn't matter what it's called, right? I'm just going to show you how we might solve for the flow, the amperages flowing around this circuit. It says solve for the branch currents. Okay, so what you have here is you have a circuit that has different branches to it, and you have a flow coming down here. Now that's a battery, so you figure the battery is going to have its way, and it's going to force a flow. And the convention is that the current is coming out the negative terminal. You have a flow of electrons coming out the negative terminal. So that blue arrow is a current, and I'm going to call it A because I don't know what it is. So I'm going to call it A. Now the idea is this is like a pipe. It's like a tube. It's like a garden hose. This is all the same current all the way to there. It's all the same current. But then it's going to split, and some of it's going to go up this way, and some of it's going to go up this way. So let's call this, I don't know, how about B? That's not a bad name. How about C? So that'll be branch current B, and that'll be branch current C. And then you could probably imagine it's going to kind of maybe, I mean, you know, and the other thing too is I'm kind of taking guesses as to which way the flow is really going. Why am I not worried about guessing wrong? Well, the wonderful thing about algebra is that if you guess wrong, you just get a negative answer. The number will be the right number. If it's negative, it just means, oh, by the way, your arrow's backwards. I've always loved that about algebra. It knows what's going on. Anyway, we should give these currents names. About like D, E. You have to give them different names because, you know, you can't just say that's X, that's X, that's X. I still don't know what this is, so X, X. You can't do it because if you're calling all of these different things X, what you're saying is that they're all the same. They're all X. So as soon as I find X is 4, you're trying to tell me they're all 4? It's like, we don't know that. They're probably all very different. So you have to use different letters, hence the old systems of equations trick. And then, you know, we've got this little, these are resistor symbols, by the way. It just means that, you know, the flow can go that way and there's something there. It could be a light bulb. It could be whatever. And well, let's just kind of say it's going that way. And we got to give this a new name. So how about F? So we've got 6, A, B, C, D, E, F. We got 6 branch currents. We need to solve for them. How do you do that? You find 6 independent equations. If we have 6 independent equations, then in principle we're done. 6, and I say independent because you don't want to just, you know, you write the same equation, make it look 2 different ways. That doesn't work. Independent equations. Now there's a couple pieces of, how should I call this, electrician wisdom. If you take our Math for Electrician course, you learn these things, but they're actually pretty intuitive. There's one that's called Kirchhoff's current law, KCL. Very, very intuitive thing. It just says that at a junction, where these currents come together, like, come on you. Okay, so like here, this is called a junction. You've got some flow coming in, and then you've got 2 flows leaving, right? So A is coming in, and then you get 2 flows leaving, B and C. That's what Kirchhoff's current law basically says, that what goes in must go out. The total of all flows going into this point, this junction here, has to be the same as the total of all the currents that are leaving. And so A must be B plus C. Now I'm going to standardize this equation this way. I'm going to say A minus B minus C equals 0. Because as you know, when we do our systems of equations, we usually like to have all of our unknowns on the left, and then we'll set up a matrix where we have constants, just numbers over here. So I'm getting the equation ready to put in the matrix. So anyway, that's our first equation. Boom. That wasn't so hard. We got 1 equation. Let's go get another one. So I'll look at a different junction. Maybe I'll look up here. There's another junction. Notice what's coming into this junction is I got this current and this current both going in. So that means D and E both go in, and they add up to What's this current? This is the A, right? It's the same all the way from here to here. This is all an A. This is all one tube. It's all going to be the same flow. So the D plus the E has to add up to A. So the standard form for this would be A, and then I'll subtract D, and I'll subtract E on both sides, equals 0. Look at that. We got 2 equations already. We're moving now, huh, folks? Okay, so let's get some of this green stuff out of here. Might be nice to have one more equation involving, like it'd be nice to get this F in there somehow, this F flow. So what I'll do is I'll grab, doesn't matter which one did I grab before, because it doesn't matter. I'll grab this junction here and say, okay, who's coming into the junction? C's coming into the junction. Who's leaving the junction? Who's leaving the junction? D and F are both leaving the junction. So the C goes in, the D and the F both go out, and so this equation will become, let's see, a C minus a D minus an F equals a 0. 3 equations down, 3 to go. Now that's one of our electrician kinds of principles, if you will, is the flow going into a junction has to equal the total flow going out of the junction. There's another one. This is called Kirchhoff's voltage law. So maybe I'll write down Kirchhoff's current law. That's where these all came from. Now there's another one called Kirchhoff's voltage law. And it basically says that you can't walk to school and then come home going uphill both ways. You can't do that. In other words, if you went uphill one way, you must have come downhill the other way. What's that got to do with electricity? Well, voltage is kind of like going up and downhill. If you go up in voltage, you can think of that loosely as going uphill. And if you go down in voltage, it's kind of like going downhill. So anyway, around any closed loop, around, going to school and home or something, around any closed loop, how should I say this? There's no change in voltage. Total voltage change is 0. Total voltage change is 0. So let's walk in a loop. How's about? So I'm going to start over here, and I'm going to walk maybe, let's see now here. I'm going to start here at the battery, and I'm going to mark around like this, like this, like this, like this, like this, and then I'll be back where I started at the battery. So I went up by 12 volts. That's what I started with. That's what a battery does. It pumps up the pressure. So it pumps up the voltage, 12 volts. And then I come around here, and when I get over to here, okay, this is a resistor, and that 3 is supposed to mean 3 ohms of resistance. And what that means is there's a thing called Ohm's law that says that the voltage change there is going to be 3 times the current. You take the rating of the resistor in ohms, 3 ohms, you multiply it by your flow in amps, which is the C. We don't know what it is yet, so it's just C. And anyway, when you multiply those two together, that's your voltage change. That's your pressure drop. So we lose 3C volts there, and then when you come up to this one, you say, oh, 5D. I'm going to lose 5D right there. And notice that that's basically it. I gained 12. I lost 3C. I lost 5D. I'm back where I started. So this all has to add up to 0. So let's see here. I'm going to put this equation in sort of a standard form. A minus 3C and a minus 5D goes on one side of the equation, and then I'll subtract 12 on both sides. Call that my equation 4. Okay. So once you see how to do that, you can just say, okay, let's turn the crank and do that a couple more times. You got to walk a different path, but I'll start with the 12 volts, and this time I'll go up this way. That'll be a different equation. Let's do it. So I got 12 volts. The battery pumps up the pressure by 12 volts. And then when I take my right turn over here, I'm going to drop, because I'm going across a resistor, I'm dropping in pressure, just like if you're blowing across a straw, or blowing through a straw, you're dropping in pressure as you go across the straw, or through the straw. Anyway, minus 6B. And when you come up through that one, you're going to lose 3E. And then you're back to where you started, so it equals 0. Let's code this one. A negative 6B, a minus 3E, and I'll subtract the 12 on both sides. There's my 5th equation. 1 to go, folks, 1 to go. Okay, so how can I walk a different loop? I'd like to do this voltages going up and down thing again, but I need to walk a different loop. So here's what I'll do. I'll go through the battery. I'll come up this way. I'll cut across the middle, and then I'll come up this way. That's a different loop. it involves the F. It's going to be a different equation. It's going to work. It's going to work, folks. So again, I start at the battery and I say pump up 12 volts. Cool. I'm coming up through the 3 ohm resistor, so minus 3C in the voltage. Now I'm coming across this F thing in the middle, so that's a minus 1F because the resistor says rated 1. Minus 1F. Okay, cool. And then I'm going up here and I'm going minus 3E. And again, that all equals 0. So this is going to look like what? Like a negative 3C and a minus 3E and a minus F is equal to a negative 12 again. Cool, so those are all Kirchhoff's voltage law equations. I've got 6 equations. I've got 6 unknowns. We're almost there, folks. We're almost there. First thing I want to do is I want to code this into a nice little matrix. So an augmented matrix. So think of this instead of X, Y, Z, and so on. Think of this as the variables are A, B, C, D, E, and F. And I'm just writing that there to kind of keep track of, help me keep track of my equations. So equation 1 says 1A minus 1B minus 1C, there is no D, there is no E, there is no F, equals 0. Get it? I'm setting up one of those augmented matrices. And you got to have the, the bar here, and then this is what the things equal. So A minus B minus C equals 0. That's what that row says. Boink, boink, boink. Okay. Where's equation 2? It's this one. Okay, so that's a 1A minus a D minus an E equals a 0. So put a 0 there, 0 there, 0 there. Equation 3 starts with us 1C minus a D and minus an F, which is over here. And that equals 0. Okay, 0, 0, 0. Doing pretty good. Now I guess this is a little premature to put the end of my matrix yet. I still got three more equations to enter here. I got equation 4, which starts as a minus 3C minus 5D equals a negative 12. That's a 0, that's a 0, that's a 0, that's a 0. Equation 5, I have a negative 6B, negative 3E, negative 12. Boom, 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 boom. And the 6th equation, I have a negative 3C, a negative 3E, and a negative 1F, and that equals a negative 12. Put a 0, put a 0, put a 0. Now we are ready to solve. Cool, we're ready to solve. Oh, you're going to like this. You're going to like this. You ready? You want to solve? I'll show you how to solve. What you do is you get out your browser. Now, I really hope I can do this. Get out my browser. Boink, get out my browser. Where's my browser? Give me the browser. Browser. Go to Safari. I want my browser. Okay. So if you go to the biffjbiffson.wordpress.com site, which is up there. Whoa. That's not what I wanted. Can I just undo what I just did, please? Anyway, yeah, you go to this site, biffjbiffson.wordpress.com, and you can go to various lessons here. Here I am on lesson 41. And when you go to lesson 41, you'll say, hey, man, look, we're doing some stuff. We reached the capstone. And come down here where it says Matrix Solvers, Online M School. Do you see this one? I'm about to click on it. Online M School. Boom. This is where you want to be. So this will give you up to 6 equations, 6 unknowns. So you just enter your equations right here where it says change the names of the... Who cares about changing the names? I'm just going to say the number of equations in the system is, and I'm going to pick a 6. We got 6 equations, 6 unknowns. And now I'm looking at the matrix that I just drew, and I'm saying, okay, let's put a 1 here. Did that read a 1? I think that's an I. Guess I have to use the keyboard. So that's it's a 1. What that is? It's a 1. Oh, come on, backspace, backspace, backspace. Okay, it's a 1. Got it? Okay, cool. And then this is going to be a negative 1. So let's see now here. That would be a negative 1, right? Right. And then we have a negative 1 in the C column, so that would be here. Negative 1. And then it's all zeros from there. I've just entered my first equation. Cool. My second equation was a 1A, so come over to here. And again, I have to use my typer thing here. So put a 1 in the A column, put a negative 1 in the D column. That would be over here. Make that a -1, -1. And then make a -1 in the E column, which is this one. -1. This will be easier to type if you have a typer. Third equation, I need to put a 1 in the C column, which would be this one. Put a 1 right there. Hey, where's my keyboard? Put a 1 right there. Yep. Put a -1 in the D column, which would be here. So hopefully you've got that matrix right in front of you so you can verify what I'm doing here. Then a -1 in the F column. This is the third equation, right? Yep. -1 in the F column, which would be over here. Make that a -1. And then that equals 0. So we're good. Okay, cool. Maybe I can scroll this website up a little bit. Okay. Fourth equation, I need to start by putting a -3 in the C column. That would be here. Put a -3, huh? Okay. -3. And then put a -5 in the D column, which is here. -5. And then put a -12 on the right. -12. What's the W doing there? 12. Okay, -12. Next column, -6 in the second row here. -6. Okay. -3 in the E column, which is going to be this one. -3, right? -3. -3. And then -12 over here again. Right. So -12. Right. Finally, a -3 in the C column. That would be this one. So, -3. A -3 in the E column, which is going to be here. -3. This is taking longer than I thought it would. Put a -1 right here. It's still pretty fun though, right? You just type all these numbers in. And then I got a -12 over here as well. Negative. And if you're still with me, now comes the golden moment. See that part where it says solve the system? Boink. I said boink. Boink. Whoa, it did it. It solved the system. Not only that, but it shows you the steps, for goodness sakes. It shows you the steps. Notice it gives you these nice row operations and everything. And then when you get to the bottom, it should have the answer in here down there somewhere. Where are you? Where's the answers? Come on, man. There it is right there. Woo-hoo. There's the answer. And it even says make a check. Come on. Check completed successfully. So here's our answers. So I copied these answers over. So I'm going to get out of this web browser now. Am I? I'm just double checking. Yes, those all match what I had before. Awesome. Awesome city. All right, get back to Notability somehow, please. There we are. So when we entered it into the online M School, so I'm going to write both websites down. Biff J. Biffson .wordpress.com. Go to the lesson 41 page and then hit the link for the online M School matrix solver. And then you enter your coefficients in. And then we got answers. We got A is equal to, and I'll just give it to you in decimal form, 3.04 amps. Woohoo! Branch B, we had 1.09. Woohoo! Branch C, we had 1.95. Branch D, we had 1.23. Branch E, we had 1.81. And branch F, we had 0.72. Now, you got to admit, that wasn't bad. You just code your equations, and boom! The online matrix solver coughs up the solutions for you. So all that hard work we did to learn how to solve systems of equations, that was kind of paying your dues. That was so you had an appreciation for what the online matrix solver is doing. And by the way, it's using Gaussian elimination, which is something we learned too. So that's kind of what I wanted to show you today, is that this is like the bread and butter activity of a lot of engineers and technicians, setting up and solving systems of equations. You can do it to solve circuits. You analyze the circuit. You had 6 currents. You wrote 6 equations. You coded them in. Boom! You got your answer. Okay, 1 example down, 3 to go. This next example is kind of near and dear to my heart. I was in heat transfer originally when I started this life. So where does heat transfer ever happen? Well, one place it happens is in your laptop. you got all these electronic chips and doodads that are all generating heat, and the problem is if they get too hot, your computer's going to go on the blitz. So you need to keep it cool. So what have I got here? I've got, imagine a chip or something, piece of computer. It needs to keep cool so that the computer doesn't crash. Okay, so this red represents a hot spot. It's 500. Oh, it doesn't matter what the actual units are or anything. We're just doing pure math example, right? Just call the temperature 500. It doesn't even matter that it's 500. It's some big number. It's the solution process that I'm highlighting here. So, and then here's where the base, where it's like glued to the whatever. So we'll just pretend that that's kind of like insulated, like glue makes a pretty good insulation. So insulation down here, hot at the top, and then somehow we've got these, we'll call it 0 degrees on the sides, right? And so the question really is, what's the temperature inside here? Like, hopefully it's not 500 anywhere. Hopefully it's less than 500, but you know, is it 400? Is it 300? What's the temperature field inside here? That's what we'd like to solve for. Now, what you can do, and actually let me use gray. What you can do, this is standard engineering procedure, is you can take your little chip that you're interested in and you kind of break it up into pieces. You draw these little squares. The official name is control volumes. So you take your chip, break it up into 8 squares. Now if you want to be more accurate, you can break it up into 28 squares or 48 squares or 108 squares or whatever. As you can see, it's all about coding the computer. However many equations you feel like coding. I'm going to stick with 8. So now there's a lot of assumptions that go into what I'm about to do, but and one of the assumptions is that we have squares. But we don't have to worry about that. Go to heat transfer school if you want to learn the real nitty-gritty behind this. But with these simplifying assumptions, I've always been amazed at how simple the process is to solve for that temperature field in there. Now, actually, I'm going to make one more simplifying assumption. Try to imagine the heat flow. Think of heat as like almost like wind, right? So this is like high pressure, low pressure. So the wind goes from here to here somehow. But it can't go through here. That's insulation. So that's like having a wall. The wind can't go through the wall. So just imagine drawing little lines of wind here. Wouldn't you expect it to kind of go something like, whew, you have a lot of wind here, whew, you have a lot of wind here. Now you can't go into the wall. So, but it's kind of got to go in and out, maybe something like this, maybe something like this. You know, just roughly speaking, the wind's got to be doing something like this. Or in this case, it's not really, it's thermal wind, I guess. It's lines of heat conduction, heat flow. It's going this way. But notice the way I've drawn it. There's a really nice symmetry line here. And so we can save ourselves some work by saying, look, whatever I see over here, I'm going to see exactly the same thing mirrored over here. We don't have to solve the whole thing. We can just solve half of it. So what I'm going to do is I'm going to set up a simpler situation. Let's set up half of it. So up here is hot, 500 degrees. Over here is cold, 0 degrees. Down here is insulation. And then how do you model this? Well, remember the idea of insulation is the flow can't go into it. You can't heat it, you know, you can't go into the insulation. Well, that's kind of what's happening here. The flow can't go across the line of symmetry either. It's symmetrical. It has to divide. It's like a dividing line. So it's almost like you have insulation here as well. So we're simplifying our model. And again, the point of this show isn't so much to have you understand heat transfer as it is to say, wow, you mean you can just do systems of equations? And it's like, yeah, you can just do systems of equations. And then watch how easy it is to code it. So basically, this temperature is going to depend on the temperature that it sees to the north, to the south, to the east, to the west. Same for all of these temperatures. This temperature is going to be the average of what it sees to the north, to the south, to the east, to the west. Now, you might be asking, well, what temperature is it seeing on all sides? Well, T1 is seeing the 500 degrees to the north. It's seeing T3 to the south. It's seeing T2 to the east. What's it seeing to the west? Well, since it's basically insulation. It's kind of like looking at itself in a mirror. Well, it is. It's a line of symmetry. Notice that if you have the same temperature here and here, there's not going to be any heat flow. You don't have heat flow unless something's hotter than something else. That's how you have heat flow. So you can just kind of model the insulation by saying, oh, that's a T1. And then here's T3. That's going to see a T3 to the left. It's going to see a T3 down here. The T4 is going to see a T4 down here. And I think what I'll do is actually, I'm going to erase the way I drew these things. And I'm going to say that this is 500, this is 500, this is 0, this is 0. Okay, and now I think it's easier to visit these 4 little temperature zones and write their equations. So looking at temperature 1. Temperature 1 is going to be the average of what it sees around it. It sees a 500 to the north, it sees T2 to the east, it sees T3 to the south, it sees T1 again to the west. Average those all up. Now if you were to kind of trust me here, if I rearrange this equation, I'm going to, let's see, I'll multiply both sides by 4. Okay, and now I'm going to basically say, okay, subtract T1 on both sides. I've got a not a negative. I have a 3T1 minus a T2 minus a T3, and I'm going to leave that pure number on the other side, right? Because that's what we like to do for our systems of equations. We have the variables over here, the x, y, z, the T1, T2, T3, T4, and then these are just numbers over here, the leftover numbers. That's one of our equations. Okay, now you visit T2 and you say, what do I see? Well, T2 is going to be the average of what it sees. To the north it sees 500, to the east it sees 0, to the south it sees T4, to the west it sees T1. Add them up, divide by 4. Okay, let's simplify that equation. Multiply both sides by 4. Do some subtracting and stuff. Negative T1 plus 4 T2 minus T4 is going to be equal to 500. There's our second equation. Third equation, now we're looking at T3 down here. What does T3 see? T3 sees T3 is going to be the average of what it sees around it. It sees T1 to the north, it sees T4 to the east, it sees itself to the south, and it sees itself to the west. Add those all up, divide by 4. Now multiply both sides by 4, do some subtracting. We got a negative T1, and then we got a plus 2 T3, and then a minus T4, and this is equaling to 0 actually. That's my equation 3. One more time. The T4 sees around it. It sees a T2 to the north. It sees a 0 to the east. It sees T4 to the south. And it sees T3 to the west. Add them up, divide by 4. Okay, so 4 times T4 is equal to this stuff. Do some subtracting. I get a negative T2, get a minus T3. Then I'll have a plus 3 T4. And that equals 0. And that's my fourth equation. Okay, let's go back to a nice blue color. Take those 4 equations, code them in our matrix. So this one, I have a 3T1 minus T2 minus T3, 0 times T4, and that all added up to a 500. There's my first equation. Second equation, a minus 1T1 plus 4T2, there is no T3, minus 1T4, and that equals a 500. Cool. Equation 3, I have a minus 1T1, no T2s. I have a 2T3 and a minus 1T4, and that equals a 0. And the fourth equation, no T1s. I have a minus 1T2, a minus 1T3, and a 3T4, and that equals 0. There's our matrix. Go back to Online M School. I don't think I'll do that here. If you just go there yourself, you'll say, oh, I can just enter this myself now, can't I? So I'm just going to double check that these are the equations that I set up before. Make sure I'm not showing you giving you a bum steer here. No, those are exactly the equations I used before. And so the equations you're going to get, or excuse me, the answers you're going to get, and I rounded a little, but you're going to get 333 degrees, you're going to get 250 degrees, you're going to get 250 degrees, and you're going to get 167 degrees. Let's bring those back up here. What's that saying? Well, if I erase all, well, I think I will. I'm going to erase, I'm going to erase these things. And I'm going to put the actual answers in here and see if they make sense to you. So T1 came out to 333 degrees. These both came out to 250. And then this one came out to 167. What do you think? It's good to chew on your answers and make sure they seem to make sense. I think this is at least physically realistic. It's believable. Notice that the coldest temperature is the one that's closest to the 0 and farthest from the 500, right? So that makes sense that that would be the coldest one. And then the hottest temperature over here is closest to the 500 and furthest from the 0. So that makes sense that that would be. And then look at this beautiful symmetry. It's 250 right across the middle, which suggests that the heat transfer is doing something like a really nice, it's just crossing beautifully like that. I love this stuff. Okay, well that was a nice example. I hope you had fun. You can analyze all kinds of heat conduction problems with this simple thing. Okay, so now that we know how to do temperatures, what do you say we do tomorrow's weather forecast? That sounds worth doing. Probably going to need a slightly bigger system of equations. In fact, the way they typically do this is they split this country or this map up into, and I bet you it's more than this too. They break it up into a really small grid. And then what you basically have is you have, however many different temperatures you got here, one for each square on the grid. 10,000 temperatures with 10,000 equations, 10,000 unknowns, something like that. Let's just zoom in on a part of this. So imagine there's this spot where you have temperature number 317 right here. That's going to be, this one. Temperature 317, and it's going to depend on what does it see to its north. Temperature 217. What's it see over here? It says temperature 318. Over here is temperature 216, and down here is temperature 417. Right? You get the idea. And then you say, well, I know that temperature 317 is going to be, and just to be kind of general about it, it's going to be some number times the temperature it sees to the north, plus some other number times the temperature it sees to the east, plus some other number times the temperature it sees to the south, plus some other number times the temperature it sees to the west. Now, the tricky part is trying to figure out, well, how in the world do we write these coefficients? And it's not easy. You have to go to like meteorology school, learn to be a weatherman, and you have to take into account all kinds of things like wind, humidity, what else? Cloud cover. I mean, you can imagine the variables. There's a million of them, right? Has a volcano erupted recently? That kind of stuff. Just everything. All this kind of stuff. Phase of the moon. I mean, I don't know. All kinds of stuff. Well, probably how strong is the sun? That would be an effect, right? Sunspot cycles and all this other stuff. So anyway, you do physics. You have to do physics to come up with, basically, you come up with little formulas and arguments and justifications for, so that's what A is, B is, C is, and D is. And that would be, for here. And it's probably a different A, B, C, and D when you're over here, and so on. But we're not going to do that. I just wanted to make the point that it really is kind of the same thing. You want to do a weather forecast for North America, the continental U.S. or something for tomorrow. It's going to be a very big system of equations. I mean, that's, you hear them say it all the time. The models are saying. What they mean by models is they mean somebody set up a system of equations. They had to kind of come up with, what are we going to say about this A, this B? What are we going to say about the effect of humidity? What are we going to say about the effect of cloud? What are we going to say about all these things? That's what they mean by the models. And then they run the models, and then they hope it seems to be working kind of okay. And it's, the more they do it, the better they get at it. And they're never really going to be perfect at it. But, you can kind of sort of make a living at it, I guess. You can make a living at it. But it's not just weather, it's anything. Spread of COVID, it's the same thing. Surely climate change, it's the same thing. Anything, the spread of, I'm trying to think. How about just the spread of plastics in the oceans or whatever, the migration of butterflies? I don't know. So for anything you want to model in this world, anything newsworthy, This systems equations is the thing. They usually call it linear algebra, which is funny because it doesn't mean what you might think it means. Linear algebra doesn't just mean equations of straight lines. It means all this matrix type stuff. But it's loosely speaking, it's systems of equations, systems of linear equations, linear algebra. Anyway, that's all I really wanted to do with this was say, hey, ain't that cool? Now you can, well, if you don't really understand, at least you have a pretty good insight into what's going on with all these models out there in this world. Exciting stuff. Okay, so we have to end with this one. So you might have noticed on page 1 I said 3 interesting examples and 1 boring one. Yeah, this is the boring one. Because it's just the old pennies, nickels, dimes, quarters, and half dollars. How you go from predicting the weather across the entire nation to pennies, nickels, dimes, quarters, and half dollars is like, it's like an anticlimax. But I need to do this because in my experience, a lot of people do struggle with this. So we need to get one more example up there that people can refer to. So what do we got going on? We got pennies, nickels, dimes, quarters, half dollars. We got 5 kinds of coins. So we're going to need to set up 5 equations with 5 unknowns, and we can of course code it on the online M-School or whatever, code it on some online. So the exercise for this lesson has become not so much, hey, figure out how to solve the system. It's simply, how do you set up the system? And then we'll ask the thing to solve it for us. How do you set up the system? Well, again, we got 5 things to solve for. We're going to need 5 clues. Here's our 5 clues. 75 coins altogether. What's that telling me? That's telling me that the number of pennies plus the number of nickels plus the number of dimes plus the number of quarters plus the number of half dollars adds up to 75. That's equation 1. So notice what P is. P is the number of pennies and so on. Remember that thing I said a while ago about you have to make sure the units are the same all the way across your equation, right? I've seen people write $12.82 over here. But that's not what you're going to write over here, because P does not stand for dollars, N does not stand for dollars. 1282 is in dollars. Okay, so that it's just, these are just counting coins. How many pennies, how many nickels, how many coins? 75. Okay, so that's your first equation right there. Okay, that's now the second equation. Okay, now we're talking dollars. So how many dollars have you got? If you have P pennies, well, each one's worth $0.01. And then you got N nickels, well, each one's worth $0.05. You got D dimes, well, they're each worth $0.1, and so on. Plus the 0.50H. Now that's dollars, that's dollars, that's dollars. And so this is adding up to the $12.82. There's our second equation. So that's pretty cool. Got to admit, it's faster to write the equations than it is to solve the system. All right. C, the number of quarters is 1 less than double the number of half dollars. Fly carefully here. You know it's got something to do with a 1 less, something to do with a double, blah, 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 blah. Make sure you put them together very carefully. Actually, I see the word is. That's usually a pretty good sign of where the equals goes. So the number of quarters is, oh, that's great. 1 less than means you're going to take 1 away from something. It's not this. It's 1 less than. If I got 1 less than you, then I'm going to figure out how many you have, and then I'm going to subtract 1 from that. Get it? So 1 less than means you're going to subtract 1 from. 1 from what? From double the number of half dollars. Well, here's the number of half dollars. Here's double the number of half dollars. And here's 1 less than double the number of half dollars. Okay, so I hope that kind of goes in and you understand what I'm saying there. So to write this equation sort of in nice form, I'm going to put the Q, I'm going to subtract 2H on both sides and say it equals -1. Call that my equation 3. Next, 2 more nickels than dimes. 2 more nickels than dimes. Okay, you got nickels, you got dimes, you got a +2 in there somewhere. How do you convince yourself of which way to do it? Well, let's see. You got more nickels than dimes. It says 2 more nickels. More nickels than dimes. More nickels means that the dimes is so small you have to add 2 to catch up. It goes like this. Nickels equals dimes plus 2. Which if I code that, I'll put the N, the minus D, and that equals a 2 on the other side. You want all your letters on one side and your numbers on the other, basically. 4 more quarters than pennies. Okay, one to go here. So 4 more quarters than pennies. So again, the quarters is bigger by 4. So the pennies is, I don't know, but to get the quarters, you have to add 4 to it because the quarters is a bigger number. So that looks like that. So put the P first. I'm going to subtract Q on both sides, and then I'm going to put the 4 on the other side. Like a dat. Did I do that right? Sure. I'm subtracting Q on both sides, and then I'm subtracting 4 on both sides. P minus Q equals -4. Yep. Good. Yep. And then you just kind of, you can write out your matrix now. You can say, well, what have I got here? My first equation is 1 pennies, 1 nickels, 1 dimes, 1 times quarters, 1 times half dollars, 75. Next line, 0.01 times this, 0.05 times this, 0.10 times this, 0.25 times this, 0.50 times this equals 12.82. Next line, what have I got? I've got a 1 times the quarters. Let's see, pennies, nickels, dimes. 1 times the quarters minus 2 times the half dollars is a -1. This one, 1 times the nickels minus 1 times the dimes equals a 2 on the other side. So I should really be filling these in with zeros. And then the last one, pennies minus quarters, no nickels, no dimes, minus 1 times the quarters, no half dollars. That's a -4. There's my 5 equations with 5 unknowns. Let me just double check that that's exactly what I wrote before. 175, yep. 0.1, yep. 0, 0, 1, -2, -1, yep. 0, 1, -1, 0, 2, yep. 1, yep. That's cool. So you go to the online M school, you get out your answers. Your answers are going to be, you've got 17 pennies. You've got 14 nickels. You've got 12 dimes. You've got 21 quarters. And you've got 11 half dollars. And it wouldn't be a bad idea to get out a calculator and say, okay, this is 17 times 1 cent plus 14 times 5 cents plus 12 times 10 cents plus 21 times 25 cents plus 11 times 50 cents, and make sure it comes out to the 12.82 that we're supposed to come out to. And I'm willing to bet. All right. So with this online matrix solvers, you just code your equations and you fly. Nice way to make a living, eh?